right, so we have this investment problem, right? So remember we've got two arms, two investment strategies, and that we can try over and over again. So it's it doesn't really fit Wall Street very well, but it's let's just think about Wall Street as we do this. And of course we don't know the future. We don't know how much money we're going to make. So we estimate. So there's be careful with my notation. So we have our return is this if we pull the ith arm, and so when we do this, maybe we get lucky, make a lot of money, and at the same time, we learn something about the average here. So the expectation of y well, actually, I should be careful here. I want to be careful before I take expectations. In this model, so there's we want to be able to place this in the context of the course so far, and so we have to model whatever this mean is by Gaussian integral. So I take expectations. I don't want to take expectations over the x's because this happened. The next one next year happened. This is the stock of Walmart and Cisco, and that's reality. I'm not going to average that out. So when I take expectations, W has a zero mean. That's it. And W is independent of x. And then we can use the machine of the course. Okay? All right, so we can go through, we can compute through our, under these Gaussian assumptions, we can compute the conditional distribution of x using the common filter, and we're going to generate estimates x hat of t of x hat. Yep. You're about to ask a question, but
that xi is independent of time.
But x is independent of time. That's right. That's right. The y is dependent on time. My return depends on time because it's the xi plus and so, but under these Gaussian assumptions, we'll write down the model. We'll write down the filter in a moment. But I promise you, we can compute the optimal conditional distribution of x hat of t. That's the conditional mean. So the conditional distribution conditional distribution of x, as you say, the static vector x, two-dimensional vector x, it's Gaussian with mean x hat of t and covariance sigma of t. Okay? And the Kalman filter gives us this, okay? And that's the beauty of Gaussian assumptions, is that just two parameters, the conditional mean and the conditional covariance, completely determine a Gaussian distribution. And that's why the Kalman filter is so powerful. So the question out of the CEO is, what would you do with this information? I've got the optimal estimate. What would you do? You know, I want to pick the one with the biggest return. You're given this optimal estimate of x1 and x2. It's the optimal, the best estimate you can have. What are you going to do? I'll put it another way. Somebody told you x1, x2, what would you do? All right.
But shouldn't you take into account sigma? Because don't you also have an estimate of how noisy x hat is? So if you have a huge variance on x2, but it's larger.
But by making your shareholders uncertain like that, you'll get fired as a CEO. You'll lose your job. And you'll get no bonuses at all. So there's uncertainty you have to deal with as well. Yeah, that's true. All right. So anyway, so stew on it some more. Let's go through and work out what this optimal filter is, and then come back to this point and everything else. And I you know, I'm doing this in part to confuse you. But anyway, let's just look at this again. So this doesn't yet look like a linear system in the form of looked at before. We have to put this in the notation of the estimation part, and then we can write down a Kalman filter. Okay? So how can we do that? So as was pointed out, this is a static system. X doesn't change. So the state dynamics are pretty simple. You know, it's very much like that parameter estimation problem I mentioned before. And we're supposed to have y of t supposed to have y equals cx plus w. And so now we've got to design a C matrix that's consistent with this problem. This is if and so that's easy, right? So x is a column vector, and c is a row vector, and obviously c is just going to pick out the right index. So if you pull the first arm, then c is equal to 1, 0, means I pick up the first element. Okay? So there it is. You know, I've got my A matrix is 0. There's no driving noise. I didn't need it. There's no state noise. I've got observation noise. I can write down the Kalman filter. And you know, this is when I want to just, you know, cry because it's just ugly. So I'm not gonna. I won't write down everything. Okay. Ouch. Let's see. So what is it? So the Kalman filter so that we first follow the state dynamics, and then you have a gain. of a gain times this innovation. And all right. And then y of t plus 1 given t, it's given right there. The estimate of this given t is 0, so you just get c times x half. And sorry, yeah. Okay, and I guess that's good. Let me see. But you can see how the proof would go through. Remember, I said you can generalize the theory to include, for example, c of t depends on time, and you can just see how right away you can take the same steps I took before. That the initial distribution of y at time t plus 1 given t is going to be Gaussian with a certain mean. And the mean is c of t times x out of t. All right. So the gain, this is where things get ugly, but they'll get simple fast. Yes.
Why do we need to update x when x is deterministic? X of t plus 1 is x of t.
These are by estimates. So the whole goal is to estimate x. Yeah. So x is not deterministic. So x of 0 is distributed n, let's say 0, 0, comma, some sigma 0. I'm going to take sigma 0 to be diagonal. Yeah. So that's really important. Yeah. So if it was deterministic, I couldn't even talk about estimation. The conditional mean would be the number. I have to put in a phony prior, a Gaussian prior, in order to apply this thing. So it's still a stochastic process, even though it's constant. So something can be random and constant. All right, it's definitely worth repeating that. Now, so this is the general update equation for sigma, but the noise is 0. And the A matrix here is the A matrix here is the identity matrix. So it simplifies quite a bit. And when you put all this together, and you do a bit of algebra, what do you get? Let's see, what do you get? You get the gain, a whole bunch of things cancel out and move around. And do you mind if I don't do the algebra? You can go through and simplify this and get that gt plus 1 is equal to this inverse is a scalar. Which still looks pretty ugly. Almost there. So the thing that's missing, we really still have to understand sigma in order to understand the gain. And we can do that pretty easily by substituting again. And again, I don't want to do the algebra. If you write this down, so if I look at this equation here, I get sigma t plus 1 given t is equal to the old sigma, and then minus something fairly ugly. And oops, stop, don't look. There might be a typo here. Just the minus signs are missing. Okay, so sorry about that. There's some minus ones here. I'll rewrite this. So that's a CFT transpose. Column vector, row vector. Column, row, that's a matrix. So what have I done here? I've just substituted. So I've taken the expression for G and plugged it in. And this is GT plus 1, that's GT. And so if you take this expression for sigma and you plug in this for GT, not GT plus 1, you'll get this after some algebra. Okay. All right. Now, let's just stare at this a bit more.
Shouldn't the sigmas be t given t minus 1?
Probably. Yeah, I was testing you. That's right. I'm gonna soon rewrite it. Yeah, I deserve to be tortured. Sorry. Yeah, is that right? Looks good enough to me. Okay? But the thing is that now we just look at this formula for C. You know, we're starting up with an initial covariance matrix that's diagonal. And if you look at this equation long enough, you'll see it preserves diagonal matrices. So sigma is diagonal for all time. And what's actually happening with this thing? If you take this matrix times itself, you'll get a diagonal matrix of this form. Because this times this is 1, 0, 0, 0. And this times itself is 0, 0, 0, 1. It's just like that. So just look at this definition, you get this. And so basically I have this diagonal. If this is diagonal, that's diagonal, that's diagonal. The thing in the middle is diagonal. You add all these together, you get a diagonal matrix. And so you get some scalar equations. So if you write down then that sigma t plus 1 given t, if you use this notation now, just to emphasize the fact that we now know it's diagonal for all time, just prove that by induction. If this is diagonal, then this is diagonal. And you get scalar update equations. This whole thing collapses too. So you get a contraction term if you pull for sigma squared 1, if you pull the first arm. And the way this is structured, if you didn't, that's 0. And this whole thing gets nulled out in the northwest corner. And so if you miss the t there, it should be t minus 1. It did it again. That's what you get if you go and play with this equation. Basically, I end up with a sigma squared of t minus 1 over here. I have 1 minus the reducing algebra. It's a bunch of annoying algebra you get that.
That will also be t minus 1.
What's that?
Bottom also. Bottom.
Oh, the u's.
No, denominator.
No, the u's too. The u's too. Everything should be. I'm missing them all over the place. I'm sorry. I don't know if I'm bored or just sloppy. I don't know. The algebra really kills me. I hate it. I wish I could just, snap my fingers and put it on the board. See, there's a t minus 1 here. So there's going to be a u. Everything's t minus 1, t minus 1, ut minus 1. But so you notice the variance stays the same if I didn't pull the arm. Well, of course, I didn't learn anything. I didn't pull the arm. I didn't see anything. How could anything change? It goes back to your point. And so these things are crucial. Now, here's something. This looks pretty ugly, doesn't it? How do you get any intuition about what's happening? Well, let's look at 1 over sigma squared 1 of t. I'll get a sum of 2 terms divided by a product of the same terms. So what I'll get is a 1 over sigma squared 1 w. The ratio of this is just the sum of the reciprocals. And in fact, given the form here, I could even change this and just to say that's just that. That if u1 is 0, I stay the same. And if u1 is 1, take a look. Flip this over, you'll get this. Just testing here. Now that looks nicer, because now I can iterate that something is equal to the previous thing plus something. And I can go back and I find that this is equal to 1 over sigma squared 1 of 0 plus 1 over sigma squared w times the number of times that this is 1. So I'm going to go back and I'm going to iterate this equation. I'm just going to get a sum of these terms. And the sum of these is just the number of times I've pulled them. Up to before time t, for t less than t1. I'm very sorry, for before time t. All right? So that's nice. And so this is going to blow up and so forth. So when you finally break this all apart, which is really, really painful to do, And that's why, can you imagine, oh, I don't want to do the algebra. You know, if I go through now and I plug in this formula for sigma into my state, estimate and all of this, I'm going to get something. And what I'm going to get is essentially Monte Carlo. So, yes, sigma 1 of t, sigma 1 squared of t. Let's just write it down for posterity. It's going to be that. Flip it over. So I'm going to write this down again. I still want to do the algebra. Observation times 0, no way. Okay, so the alphas and betas are the sigma squared w's and the sigma squared 1 zeros and all that. I give you formulas for them, but I don't really care. What you're getting is Monte Carlo, basically. It's a sample path average. You know, the optimal estimate, there's going to be some perturbations because of the initial uncertainty and because of how big sigma squared w is going to change the filter slightly. But it's just an average. You know? So when T1 of t, the number of times R1 is pulled is large, this constant alpha disappears basically, the betas cancel out. It's just 1 over the number of times I pulled the arm, and then you're summing over y of t at those times at which you pulled the arm. That's standard Monte Carlo. It's what any CEO who has access to Microsoft Excel would do. You'd look at your earnings every time you tried that particular stock, and you'd average the results. So it's just a slight modification of Monte Carlo.
That's x1 then, right?
And that's x1. Thank you. Sorry. Sorry. All right. So let's go back. So this is basically, why am I going through this? I just want to show you can just mindlessly, and with a little concentration, you can take the Kalman filter equations, apply this in. I mean, it's pretty disappointing to get something you would have just done anyway. You just Monte Carlo. But in other examples, it's not. I mean, if there were dynamics, you would take into account in the real stock market example, those would appear here. It would be less trivial. All right, now let's go back to the question. And now, given your point, it's maybe a little more obvious that it's much more complicated than it first sounds. So now, given these optimal estimates, I've got x1 of t and x2 of t will be similar. What are you going to do? Well, let's just look at this. Let's look at the CEO solution. Okay. Okay, I was joking. That's a CO solution. You know, basically, this is especially if you tell them this is the optimal estimate. You can't do any better. It's the optimal estimate of the state, given your observations. Then, well, if it's the optimal estimate, I'm going to take the certainty equivalence approach and take the guy who I think is going to give me the most money. And what's wrong with that?
There's a lot wrong with that.
Yeah. So tell me. You could probably say it better than me.
Well, I mean, the first thing you see that's wrong is that the only thing that matters is your initial estimate, because if one is higher than the other, then forever you will only see the one.
Yeah. So suppose x 1 hat of 0 is much, much greater than x hat 2 of 0. That's right. And let's go, and we're really, really, really pleased with ourselves. So we're going to pick, as you say, we're going to pick u1 of 0 is equal to 1. And then x hat 2 of 1 is going to be x hat 2 of 0. And again, and we're going to keep on pulling, we keep on feeling really happy with ourselves and keep getting our bonuses. And this could happen forever. It's perfectly possible this will always happen. With positive probability, this will always happen. So with positive probability, and then we know that sigma squared 1 of t, well, this t1 of t will now be t. And so the variance is going to go to 0. In fact, almost surely you will converge. And x2 hat of t will converge as well. Much faster. Yeah. That's faster than quadratic convergence. Just lock on to the optimal estimate. It's the optimal estimate. It's the optimal estimate given your observations, and you've just limited your observations to this myopic world, and that's the point. I mean, and it's like, the joke isn't that big. I mean, it really is how people think of it. They optimize based on their really narrow view of the world. I think that's a fact. And I'm not just saying that because election season's upon us, but that's part of my depression at the moment. So anyway, so definitely if x1 is bigger than x2 hat of 0, x2 hat of 0, this is really possible. When I say with positive probability this is possible, well, you'd have to have x1 bigger than x2 hat. Because given this convergence, greater than equal to, given this convergence, if x1 was less than x2 hat of 0, you get a contradiction. Eventually, you start before. So what do you do then? You say, this is where the fun is. So you can say, well, this is a partially observed Markov decision process. And let's go and we know that the belief state, blah, 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 blah. We could do that. There's no way there's anything that we've learned in this course to attack this problem. Nothing. We can come up with the optimal estimate, but it's pretty much what anybody would have come up with, without even thinking. And so how do you do this right?
Shouldn't by x1 being much bigger than x2, how big?
Oh no, I'm just here. I mean, just follow the steps. I mean, it doesn't matter. I mean,
because if we choose x2 over x1, then we're losing that.
No, I mean, if this is bigger than this, then u1 of 0 is 1, and then this is true. I mean, these steps are true. I mean, I only need that. I'm just saying that this could be much bigger than this, is all I'm saying. And that doesn't mean a thing about reality. That's all. This was poetry, not mathematics. All I need is this to be greater than, and these steps are true. Okay? I need that to be true, and I need at least that to make this claim. So if your initial guess is wrong, and you have this And actually, yeah, somebody else tell me what they would do. I mean, given this. God, man. I'll live it with these shoes again. What would, somebody, I'm sure there are a lot of ideas about it. What would you actually do given this problem?
Hope I'm not starting at time equals 0.
What's that?
Hope I'm not starting at time t equals 0.
Oh, really? No, just take my money and run. You just,
No, I'm saying if you're not at time t equals 0, you have to pick up previous history to go off.
yeah. But even then, I mean, but I'm not going to let you go forward in time. What would you do?
Pick a probability and pick the maximum with that probability and the other one with 1 minus that probability.
Yeah, the drunken CEO solution. So X, when I say CEO solution, I mean this greedy solution, where I take 1 if my estimate of the mean is greater equal to or greater than xi bar, the other I. So this is, if I is 2, I mean, by I bar, I mean 1. All right, and that's a solution that will work. And then the question is, how should you choose P? And
so you should make sure that this regret is bound, right?
What's that?
The regret is, because this is a regret.
Well, we're going to get into the issue of regret now. Absolutely.
Yeah.
That's how we're going to analyze it. So one performance criterion then is regret minimization. So that's great. So. So now this is my reward at time t. So in terms of goals now, it's really easy to make the average reward equal to the maximum. I mean, almost any idiotic thing you would do would be. I mean, as long as you do something to make sure you learn a little bit. There's lots of this. As long as what do you need? You basically need to pull each arm infinitely off. If P of G is chosen, so you maybe jump ahead a little bit. So if P of T is chosen, we've seen that if P of T is chosen so that UI of T is equal to 1 infinitely often for I equals 1 and 2, then we've seen that the covariance goes to 0, and in fact with probability 1, you're going to converge. And that's just a matter of Monte Carlo, you're just averaging. So it's just, and so you can see that just under that condition alone, the average cost, the average reward, so, really, really, a million choices will give you this. And so actually you were jumping ahead. The question is that this is too crude. In this case, I really would say that in the long run you're all dead. When we're trying to maximize the reward for the next few weeks, this average reward criterion is just too weak. And so instead you look at a finite horizon sort of condition like this, and you want to basically minimize the regret. And we can't really minimize it exactly, but at least we can minimize its growth rate. And that's the thing. So we'd like this to be equal to this for all time. That's the best. X star is the max. And rather than, since there are so many choices between this, you can look at this final thing. By the way, do you notice that this is our cost or reward at time t? And that's our steady state average reward? The mean of this looks a lot like a relative value function. So I mean, there's a tight connection there. So the average reward that's that relative value function. That's actually, so that's not very useful because h of x is the belief state. We have to lift this up to this infinite dimensional setting. So it's a pretty meaningless statement. I'm just saying that there's a connection there. And the question then is, how should I choose p, not just to get this average reward maximized, but to get this regret to grow at a minimal rate? And it turns out the minimal rate turns out to be the log of n, which is pretty small. And the way to do that is really easy. Basically, you choose p of t, so it goes to 1 just at the slowest rate possible. So what have I done here? This p of t should go to 1, right? So 1 minus p of t and maybe there's some constants in there to make it work. And that's Lyapunov. And they did better than that. It's so great. What did they get here? I just want to make sure I don't screw this up. They get not just log of n, I don't know exactly how tight the approximation is. Well, first of all, they get a lower bound for any policy. Where they're looking at a more general setting, where the rewards are ID generally distributed. Okay? So they have, it's not Gaussian at all. They look at a completely general setting. They have ideal wards with distribution μr. And xi and x star are exactly as before. So they can have, I could be from 1 to d, say. So there could be a d-arm bandit. And di, it's so beautiful. It's the distance between these distributions. Now, most of you don't know what this is. It doesn't matter. It's just a distance between probability measures that's a foundation of communication theory. It's information theory is based on this. And so it's a measure between distances. So if you might have two x's with very different means, but their distance in this relative entropy sense could be very, very small. So it's hard to distinguish the probability distribution. So learning is going to take longer. So this could be close to 0, even though the means are very large. And so that makes their correct one.
Is there xi still constant?
Well, I'm sorry. These xi's and t's are like the y of t's.
They're the y of t.
Yeah, this is sorry. Yeah, in terms of the language, excuse me. That's.
So that xi is still our xi though, right?
Yeah.
Okay, well there's something wrong because if you condition both sides on xi, only one side's a random variable. So how can you have an inequality?
Oh no. This is determined. Remember that we would we flip the coin and stay there forever.
So then I don't even have to condition. One's a random variable, one isn't.
Well, I mean, actually, the reason I went to go through all those steps, take x of 0 Gaussian, and the y of t x plus Gaussian. The reason I had to go through all those steps was to force the Kalman filter.
Right, but
in line Robbins, what they do is it's a totally different. It's not totally different.
So in their paper, the right side is not a random variable, right?
Yeah, and either is ours really.
No, but the right side, the left side is a random variable.
Yes.
Whose support is the entire.
Yeah. Well, let me write this down. So xi is equal to the expectation of xi of t. So previously, when I was in this Gaussian world and I had to say my initial x was Gaussian and all that, it was just to force this Kalman filter framework on it. But now if I just say I've got...
That doesn't solve the problem, that makes it even worse.
It makes it well, now I can't apply the Kalman filter.
No, I mean, the equality still makes less sense.
Oh, why is that?
Wait, because the right side is a constant and the left side is a random variable whose support is the entire real line. So
yeah, but the thing is that we get a lower bound for any policy, but they show with the modification,
you can't have a... But
no.
The left side is a random variable whose support is the whole...
I see what you mean.
Limit is... okay,
Yeah.
That makes sense.
Yeah, I'm sorry. I forgot the limit. Thank you.
Okay,
That's very clear. Thanks for that. So the lower bound is achieved using something like D star. There's a little bit of more fooling around, but it's basically that. Okay? And so it's the form of this solution is so elegant. That if this is small, then obviously learning is harder because it's a measure of distance, and so if the distributions are almost identical, it takes a long time to learn. So it's a beautiful result. And this is just a wonderful segue into the next part of the course. I mean, so first of all, the big moral here is that there are two issues. There's exploitation. So there was something that people call exploitation, and that's perceived exploitation. The CEO sees that the that somebody's told them that something's better than another, and he or she buys it, that the perceived exploitation will get you into trouble. But you've got, in this problem, we had this tiny bit of exploration in order to get an optimal solution, and that's the the catchphrase, the marketing term in reinforcement learning and so forth. But we see it so beautifully in this example. But there's a conflict, about when I should exploit and when I should explore, and so that'll be a sort of a theme in the rest of the course. So in the end of the course, we're going to look at methods for doing more exploring and exploiting. So we've done the exploiting already. So we've seen exploitation. That's all the MDP theory. We've got a model of the universe, and we stick in our optimal controller based on that. In this case, our model of the universe was ridiculous, so we got a bad response. And so for exploration, these are these learning algorithms. And I'm just going to fixate on a few. Q learning, TD learning, something called SORSA, because they fit in with the rest of the course nicely. And they have really beautiful mathematical foundations. They're practical enough to be used today, unlike some things that neural networks have been promoted for I don't know how many years. And still I don't know if they're practically useful or not. But these are things I have confidence in and fit in with the rest of the course. So we'll start on that next time. There's some math you need, I can write down these algorithms. But all of this has one foundation, and it's stochastic approximation. And what's stochastic approximation? It's just a tiny, tiny variant of Monte Carlo. Like here, Monte Carlo, x hat of t equals 1 over t, sum from 0 to t minus 1 of xi of t, ui of t. Monte Carlo, not t, whatever, ti. The notation I had before. You take the average of the observations, that's an estimate of the mean. Stochastic approximation is this tiny epsilon generalization of Monte Carlo. The theory, the analysis is deep and difficult, and I'll give you the main ideas. I can't, in the next 10 lectures, we can't go that deeply. But I want to give you the main ideas, and once you have this machine, it's like the Kalman filter. You can turn it loose on anything. It's just like, it's incredibly valuable. And Q learning, T learning, SORSA, they're trivial after this monster. So we'll spend a bit of time on that, and I've got lots of notes on this. And mainly, it's as long as we don't go in deep into convergence proofs, there's nothing to be afraid of. So have a good weekend. I hope to see a lot of you at the talk today. If you got my email at 2 p.m. My colleague Prashant Kent is in town. He's giving a talk on our joint work on particle filters and nonlinear filters. And if I don't say myself, it's beautiful work. It's beautiful work you'll ever see. So it's our joint work. He's a good speaker. Much better than me. He's a good and it's designed for a broad audience.